Why are inner planets rocky and outer planets gaseous? We all know the solar system contains two kinds of planets. The first four, Mercury through Mars, are quite small in size, and they are rocky planets, also called terrestrial planets. The outer four are gaseous giants, from Jupiter to Neptune. They are called Jovian planets, and they are immense balls of gas with a central core. While conditions on these planets can be very different from one another, each type of planet shares some similarities and offers its own set of challenges when it comes to exploration and observation. But where does this difference come from? Do all solar systems have rocky planets closer to their stars? Keep watching the video to get to know the answer to these questions and more. The Earth is perhaps the most important rocky planet in our solar system. On Earth, the core, mantle, and crust are divisions based on compositions. The crust is really a small part of the overall Earth's mass, accounting for less than 1%. It consists of oceanic crust, and continental crust is often more felsic rock. The crust is where we live, the place we walk on, and the most exposed layer of our planet. Then there is the mantle. The mantle is hot and represents about 68% of Earth's mass. And if you go deeper, you can reach the core. I mean, you can't really, because the deeper you go, the stronger the pressure, and you'll reach a point where you won't be able to survive anymore. But let's suppose this doesn't happen. If you could reach the core, you would see it's made of iron metal. The core makes up about 31% of the Earth. One may ask, how do we know the core is metallic? Scientists know that the core is metal for a few reasons. First of all, the rotation of the Earth gives us some hints about the average density of our planet. It can be shown that the average density given by the rotation is much more than the density of Earth's surface layers, which we can measure. The only way for this to happen is to have an interior denser than the average. Basically, if surface layers are less dense than average, then the interior must be denser than average. Calculations indicate that the core is about 85% iron metal, with nickel metal making up much of the remaining 15%. Also, metallic meteorites are thought to be representative of the core. Second thing, if Earth's core were not metal, the planet would not have a magnetic field. But we know a magnetic field exists around the Earth. A mechanism that could produce and sustain a magnetic field is the so-called dynamo mechanism. For this mechanism to act, the outer core of the planet must be liquid and the inner core must be solid. The strong magnetic field is caused by convection in the liquid outer core. Convection currents in the outer core are due to heat from the even hotter inner core. The heat that keeps the outer core from solidifying is produced by the breakdown of radioactive elements in the inner core. Speaking of Mercury, it also has a central core, a rocky mantle, and a solid crust, just like Earth. It's actually the second densest planet after Earth. It has a large metallic core with a radius of about 1,289 miles, or 2,074 kilometers, about 85% of the planet's radius. There is evidence that it is partially molten or liquid. Mercury's outer shell, comparable to Earth's outer shell, called the mantle and crust, is only about 400 kilometers or 250 miles thick. What about Venus? Interestingly enough, if we could slice Venus and Earth in half, pole to pole, and place them side by side, they would look remarkably similar. They both have an iron core surrounded by a hot mantle, and they both have a crust, which is a quite thin external layer. The crust is a sort of skin that changes form over time, causing volcanism. However, the two planets are also really different. For instance, the plate tectonics mechanism is active. It is the slow movement of continents over thousands and millions of years that reshapes the surface. This is not observed to be happening on Venus. If it did in the early history of the planet. But we observe strong volcanic activity on Venus. This could be due to subduction, the sliding of one continental plate beneath another, which can also trigger volcanoes. NASA's Magellan spacecraft saw a land of extreme volcanism. The orbiter saw a relatively young surface, one recently reshaped in geologic terms, and chains of towering mountains. Last but not least, Mars has a dense core at its center, between 930 and 1,300 miles, 1,500 to 2,100 kilometers in radius. It's made of iron, nickel, and sulfur. Surrounding the core is a rocky mantle between 770 and 1,170 miles, 1,240 to 1,880 kilometers thick, and above that a crust made of iron, magnesium, aluminum, calcium, and potassium. This crust is between 6 and 30 miles, 10 to 50 kilometers deep. The four gas giants in our solar system are Jupiter, Saturn, Uranus, and Neptune. As we've already mentioned, they are also called the Jovian planets. A gas giant is a giant planet that is made of gas. They are different from rocky or terrestrial planets that are made of mostly rock. Unlike rocky planets, gas giants do not have a well-defined surface. There is no clear boundary between where the atmosphere ends and the surface starts, and you can't walk or land on their surface. The gas giants have atmospheres that are mostly hydrogen and helium, the most common gases in the universe. Gas giants may have a rocky or metallic core, but the majority of their mass is in the form of gas. Since the pressure is really high, gas on these planets might also be compressed into a liquid state, just like mercury in a thermometer. Jupiter and Saturn probably have liquid metallic hydrogen interiors, which allows them to have a magnetic field, since liquid hydrogen conducts electricity. Scientists believe Uranus and Neptune have interiors that contain a mixture, or layers, of rock, water, methane, and ammonia. So far, we have given a brief description and overview of the composition of planets in our solar system. Now let's get to the point. Why are they different? To understand why the rocky planets are closer to the Sun, we must go back to when the solar system was young and the planets were still being born. The planets in our solar system are believed to have formed from the same spinning disk of dust that formed the Sun. This disk was composed mainly of hydrogen and helium, but also had other elements in smaller proportions. Dust particles in the spinning disk began to clump together as gravity attracted them to each other. You have to think about it as a fight. During this period, clumps of matter were trying to grow as big as they could in order to overcome the others in size, thus being the dominating objects in the disk. Over a few million years, many of these chunks had merged together, and there were about 109 objects called planetesimals, with diameters of about 1,000 meters. Over time, the planetesimals continued to collide and join together, attracted by gravity. These larger objects, about the size and mass of our moon, are called protoplanets. The accumulation of material to form planets in this way is called accretion. The solar system, in its youth, was very chaotic. All the planets, and even our own sun, were in exotic and excited states. For example, the Earth was basically a ball of lava. A long time passed before it cooled down. In the early solar system, there were many collisions and explosions and heat waves passing between them. Once upon a time, the rocky planets we see now also had huge gaseous layers around them, just like the gas giants and ice giants. However, during its angry young years, the sun let out huge streams of energy and matter into the solar system. The rocky planets, being the closest to the sun, took the full force of these streams. This made the gases of these planets part ways with them, leaving just the rocky part behind, which went on to become the terrestrial planets. The remaining 4 planets were too far from the sun to experience these streams, so they stayed relatively unaffected and formed the gas and ice giants of today. So is this a pattern that we see everywhere? Do other solar systems in other parts of the universe show the same trend of having the rocky planets closer to the star, while the massive gas giants are quite far away? The answer is no. Scientists have found many solar systems in which gaseous planets, many of which are even more massive than the gas giants of our solar system, are the ones closest to their stars. For instance, they found a lot of hot Jupiters. Hot Jupiters are Jupiter-like planets orbiting really close to their host star. The first hot Jupiter ever discovered is 51 Pegasi b. It was actually the first exoplanet to be discovered around the star similar to our Sun. It is the prototype of the hot Jupiter planets and is located in orbit around the star 51 Pegasi in the constellation of Pegasus. The discovery of this planet changed our understanding of the universe forever. When 51 Pegasi b was discovered, planetary formation theories were not compatible with a giant planet so close to its star, and it was considered an anomaly. However, since then, numerous others have been discovered, such as in the 55 Cancri and Tau Botis systems. The authors of the discovery of 51 Pegasi b, Michel Mayor and Didier Queloz, has been awarded the Nobel Prize in 2019. and new planetary formation theories are being proposed every day. Most of them take into account the dynamics of the diverse systems. For instance, astronomers have begun to revise their theories and study the possibility of amazing dynamical phenomena such as orbital migrations. But this is a story for another video. Where are the moons? Where are the rings? Let us begin with two simple statements based on mere observational evidence. All the gaseous planets of the solar system, Jupiter, Saturn, Uranus, and Neptune, have developed a ring system, while the terrestrial-type planets, Mercury, Venus, Earth, and Mars, have not. All the gaseous planets possess entire legions of natural satellites, while the terrestrial planets are almost totally devoid of them. Yet smaller, large, solid, or gaseous, all planets in our planetary system have had a common origin. Why can't Earth boast of a beautiful ring system? And why are Venus and Mercury completely devoid of moons in their sky? What cosmic law commands or forbids this? There are a lot of things that differentiate the planets. The first four are extremely different from the others, not only in appearance, but also in composition, evolutionary history, and formation, leading to a natural distinction between the inner and outer solar system. Since all planets, both outer and inner, formed from the same disk of dust and gas that surrounded the Sun, the reasons for such differentiation must be answered somewhere in the history of their formation. But when did this separation occur, and why? The most likely explanation is that there was an empty space in the disk that separated the inner from the outer disk. Such a structure must have been in the main asteroid belt, but it is not yet clear whether the gap may have formed because of Jupiter's gravitational action or because of the Sun's gravitational action. What is certain, however, is that through this dividing belt passes the so-called frost line, which is the dividing line between the outer region of the solar system, where water is found only in the form of ice, and the inner region, where water has instead been volatilized by the Sun's heat. However, things have turned out that boundary has enshrined the clear separation between the inner planets, which are denser and smaller than the outer planets, and specially endowed with a solid surface. There are, however, two peculiarities that jump out at you. None of the inner planets possess rings, whereas the totality of the outer planets do, and in addition, the inner planets are virtually devoid of natural satellites. Out of a total of 221 satellites cataloged so far, 218 belong to the outer solar system and only 3 to the inner one. Of course, it makes quite an impression to hear that all outer planets possess rings. To hear such a statement, an astronomy enthusiast left over from the 1970s would jump on his chair and shout, "What are you talking about? Only Saturn has rings." And indeed, until 1977, school books reported that there was only one planet in the solar system that could claim the title Lord of the Rings: Saturn. In fact, Saturn's rings are the most extensive ring system, so they have been known to exist for quite some time. Galileo Galilei first observed them in 1610, but they were not recognized as such until 1655, with the observations of Christian Huygens. And we have known for several decades now that they consist mainly of water ice, with the individual particles varying in size from micrometers to meters. But on March 10, 1977, there was the first small revolution. On that day, some astronomers aboard the Kuiper Airborne Observatory, an aircraft equipped for high-altitude infrared observations with a 91-centimeter diameter telescope, were tracking the occultation of a star by Uranus to study the planet's atmosphere. But when they analyzed their observations, they discovered that the star had briefly disappeared 5 times before and after the occultation by the planet, a phenomenon that can only be explained by the presence of very thin rings. Such a ring system was later actually photographed by the Voyager 2 probe that passed near Uranus in 1986. Just 2 years later, on March 5, 1979, it was Jupiter's turn to be visited, this time by Voyager 1, and again there was the surprise of discovering a ring system, albeit a very faint one. To get to the question of whether the fourth and final gas giant, namely Neptune, was also surrounded by rings, one had to wait until August 25, 1989, when Voyager 2 passed within 5,000 kilometers of the planet's atmosphere, revealing the existence of a system of faint, dark rings similar to those of Uranus. Basically, in a period of 12 years, from 1977 to 1989, the ring lords went from 1 to 4, which has confronted the astronomical community with a couple of big questions. How are these structures formed? Are they the inevitable remnant of the formation process of the outer planets, and thus were born with them? Or did they form accidentally due to different causes? Why do only the outer planets form rings? It seems unbelievable, but at present, for the first question, there is still no agreed answer. Apparently, however, everything seems to be governed by the so-called Roche limit. You'll certainly remember it. The Roche limit indicates the minimum distance at which a satellite can orbit a planet without being fragmented by its tidal forces. An object that crossed this limit would in fact experience a much stronger gravitational pull on the hemisphere looking toward the planet than that experienced by the farther hemisphere. The tidal forces would be so intense that they would eventually overcome the intrinsic gravity of the smaller body, shattering it. If the planet and the satellite have the same density, the Roche limit is worth about 2.42 times the planet's radius. Within this limit, a satellite of discrete size will then be deformed and then disintegrated, while very small satellites, those able to withstand gravitational stresses by their internal cohesive force, will be able to continue orbiting without problems. Then there is another thing. Within a disk of fragments surrounding a forming planet, matter located beyond the Roche boundary can aggregate to form satellites, while in an area closer to the planet's tidal forces prevent the formation of any satellites. But just so you can get an idea of the distances involved, here is what the limit is theoretically worth for each of the gas giants. Jupiter, 175,000 kilometers. Saturn, 147,000 kilometers. Uranus, 62,000 kilometers. Neptune, 59,000 kilometers. Well, from this data, it will be very instructive to verify, if you feel like it, that all the rings of the planets in the solar system are within the Roche limit of their planet. And this is a very strong clue indeed. So much so that based on this finding, astronomers have formulated two hypotheses that could explain the formation of the rings. The first is this. The gas giants, as is known, form from the aggregation of gas and ice contained in the disk of materials that envelop the Sun. In turn, the forming planets were also surrounded by their own accretion disk. Above the Roche limit, particles from these disks aggregated to form satellites. Below the limit, on the other hand, tidal forces prevented aggregation, and the remaining material was then confined in more or less thin rings by the action of the so-called and very small shepherd moons. Instead, the second hypothesis ventures that it may have gone another way. Once each planet had completed the formation of its satellites using all the material in the disk, one or more of them may have slipped for some reason, as is happening to Phobos, the satellite of Mars, below the Roche boundary, where, torn apart by tidal forces, it would give rise to one or more rings. An accident in the planetary system could have occurred at any time in its history, even very recently. All this would then lead us to think that it is quite normal for a gas giant to develop its own ring system sooner or later. Even though, however, the second question remains to be answered. Why did only the outer planets form rings? If the hypothesis of ring formation due to the disintegration of a satellite were true, then this would also explain why the inner planets are completely devoid of them. Indeed, the lack of rings seems to be related to the lack of satellites. Let's see how. The main fact is that the giant planets were formed in a very different environment from that of the terrestrial planets. The larger volume of space available and less gravitational interference from the Sun allowed Jupiter, Saturn, Uranus, and Neptune to form as miniature solar systems. In addition, it was much colder in the outer solar system, and all the water there existed only in the form of ice, which allowed the planets to acquire mass in large quantities very quickly. In contrast, the terrestrial planets formed much closer to the Sun, with much less material around them since the water had been turned into vapor and dispersed by the solar veto, and they grew slowly by accretion of small rocky planetesimals without ever becoming massive enough to form their own disk of gas and dust. No accretion disks then, and therefore no satellites ever had a chance to form around Mercury, Venus, Earth, and Mars. Sure, Earth has the Moon and Mars has Phobos and Deimos,
but both cases are exceptions that have nothing to do with a generalized formative process. Our moon, is formed by the occasional impact of Earth with a Mars-sized planetoid. A ring of dust and rocks also formed as a result of the impact, but in a few thousand years, or even in a few hours as one recent theory would have it, it thickened to give birth to our satellite. Similarly, the Mars satellites are merely the result of the cause of gravitational capture of two asteroids by the red planet. Nothing like those veritable satellite factories that are the outer giant planets. But wait a minute, we just said the Earth, too, was for a short time surrounded by a ring system. But then, why did they not last? The answer lies in the fact that most likely the ring formed far outside the Earth's Roche boundary, which is worth about 18,000 kilometers. If it had formed inside instead, the orbiting debris would never have been able to coalesce. And it is curious to note that Mars will also experience the thrill of seeing itself surrounded by a system of rings. It will happen in the not-so-distant future when Phobos, which due to tidal friction is also getting closer and closer to the red planet, will exceed the Roche limit and break up into a dusting of rings. Rings which will be very short-lived, however, and a slow fallout on the planet or scattered by the solar wind, which at the distance of Mars still blows very strongly.